All right, let's go. Number 10. There is no outside. The universe has no edge. This is the first theory, and it's the one that breaks most people immediately. When we say outside the universe, our brains automatically picture something like outside a building, a wall, a boundary, and then something beyond it. That mental image is wrong in a way that's hard to shake, because the universe isn't a ball of stuff sitting inside a larger empty space. The universe is space itself. There is no container, there is no wall. Space doesn't end, it curves. In 1917, Albert Einstein applied his equations of general relativity to the universe as a whole and found something unexpected. A universe filled with matter and energy doesn't have to have an edge. Space can curve back on itself the way the surface of the Earth does. Walk far enough in one direction on Earth and you return to where you started, not because you hit a wall, but because the surface is curved and finite with no boundary. The universe could work exactly the same way in 3 dimensions. Travel far enough in any direction and you'd eventually return to your starting point from the opposite direction, without ever hitting a wall and without ever leaving the universe. In 2003, cosmologist Jean-Pierre Luminet and his team published an analysis of the cosmic microwave background, suggesting the universe might have a dodecahedral shape, 12-sided, curved, finite, and with no edge. The analysis is debated, but the underlying mathematics is solid. If this is correct, asking what's outside the universe is like asking what's south of the South Pole. The question sounds valid, it just has no answer because the concept doesn't apply. Number 9. An infinite void with no properties. Let's say the universe does have an edge. Let's say space genuinely ends somewhere. What's on the other side? The most mathematically honest answer is something most people find deeply unsatisfying. Nothing. Not empty space, not darkness, not cold. Literally nothing. No space, no time, no energy, no fields, no physical properties of any kind. A state so completely devoid of everything that the word nothing doesn't even do it justice, because nothing implies a kind of emptiness that still has location and dimension. This would have neither. Physicist Lawrence Krauss at Arizona State University spent years working through the physics of what genuine nothingness would mean in his 2012 book, A Universe from Nothing. His conclusion was that what we casually call nothing is actually never truly nothing. Quantum fields permeate all of space and can never be fully removed. True nothing, no quantum fields, no space-time geometry, no physical laws, is a state we have no physical description for, because our physics requires something to already exist before it can describe anything. Here's why this is terrifying rather than just boring. If true nothingness lies outside the universe, no laws, no structure, no logic, then the universe's existence has no external support. Nothing is holding it in place, nothing is maintaining the laws of physics that keep atoms from falling apart. The universe exists as a kind of bubble of structured reality floating in an absence of everything, with no reason it couldn't simply stop at any moment. The stability of every atom in your body depends on laws of physics that have no external foundation. They work because they work, and outside the universe, they don't apply at all. Number 8. Other bubble universes expanding toward us. In 1980, MIT physicist Alan Guth developed the theory of cosmic inflation, the idea that the universe expanded at extraordinary speed in its very first moments. This theory solved several major problems in cosmology and is now one of the most accepted ideas in modern physics. But it came with a consequence nobody was looking for. Physicist Andre Linde of Stanford realized that if inflation is driven by a quantum field, quantum uncertainty makes it almost impossible for inflation to stop everywhere simultaneously. In most regions, it stops, forming universes like ours. But in other regions, the quantum fluctuations keep inflation going, producing more space, which produces more stopping regions, which produce more universes, forever. The process never ends because expanding inflationary space always produces more of itself faster than it loses territory to new universes. This is called eternal inflation, and its implications for what lies outside our universe is concrete and specific. Outside our universe, in the inflationary space beyond our bubble, other bubble universes are forming constantly. Each one is its own complete universe with its own physical laws, its own matter, potentially its own forms of life. They are separated from us by regions of still inflating space that expand faster than light and can never be crossed. But the bubbles are moving, expanding. And in 2010, physicist Stephen Feeney at University College London found 4 circular patterns in NASA's map of the oldest light in the universe that he proposed were the physical scars of past collisions with neighboring bubble universes. The Planck satellite didn't confirm the patterns with certainty, but it didn't rule them out either. Outside our universe right now, other universes exist. They are expanding, and there is no physical law guaranteeing their borders will never reach ours. Number 7. A higher dimensional space we cannot perceive. Everything we experience happens in 3 dimensions of space and 1 dimension of time, left and right, forward and backward, up and down, plus time moving forward, 4 dimensions total. That is the complete set of dimensions available to everything we can see, touch, measure, or detect. String theory, the leading mathematical framework attempting to unify all of physics into one coherent set of equations, requires 10 spatial dimensions to work. M-theory, its more complete successor, requires 11. The extra 6 or 7 dimensions the theory proposes are curled up at every point in space at a scale so tiny, the Planck length, roughly 10 to the power of -35 meters, that no instrument ever built or conceived could detect them directly. But they would still be there, real, physical, just inaccessible to anything made of the particles and forces confined to our 3-dimensional membrane. Physicist Lisa Randall of Harvard and Raman Sundram of Johns Hopkins published the model in 1999, proposing that our universe is a 3-dimensional membrane, a brain, floating in a 5-dimensional space called the bulk. Gravity, unlike all other forces, can leak between brains through the bulk. This is actually proposed as an explanation for a real unsolved problem: why gravity is so much weaker than all other fundamental forces. It might be leaking into the extra dimension and arriving at our brain diluted. Outside our universe in this model is the bulk, a higher dimensional space containing our brain, alongside potentially many others. Objects in the bulk would be undetectable to us. They would exert gravitational influence across the dimensional gap without ever appearing in our 3-dimensional space. Their presence would show up as unexplained gravitational effects in our universe that appear to have no visible source. We already detect unexplained gravitational effects in our universe. We call it dark matter. Number 6. A dead universe with different physical laws. Not all bubble universes in the eternal inflation model are created equal. When a region of inflating space stops inflating and settles into a stable state, the physical constants that govern that region, the strength of gravity, the mass of particles, the charge of the electron, are determined by where the quantum field settles in what physicists call the landscape of possible values. There are an estimated 10 to the power of 500 different possible combinations of physical constants. Each combination produces a different universe with different physics. Most of those combinations produce universes that are immediately and permanently hostile to any complexity whatsoever. Some settle with a cosmological constant so large the universe expands and tears itself apart in seconds. Some settle with gravity so strong everything collapses before any structure forms. Some have no stable atoms because the forces that hold nuclei together are too weak. Some have no chemistry because electron behavior is different. Some are entirely dark, entirely empty, or exist for only a fraction of a second before their vacuum state collapses. Outside our universe, in the inflationary multiverse, the overwhelming majority of bubble universes are completely dead. Not dead the way a lifeless planet is dead. Dead in the sense that the laws of physics inside them don't allow any structure, any complexity, any event to occur at all. Physicist Max Tegmark of MIT estimates that a universe with physical constants even slightly different from ours, within a few percent on most parameters, would not contain stars, would not contain atoms, and would not contain anything recognizable as matter in any meaningful sense. We exist in a universe so precisely calibrated that atoms, chemistry, and biology are possible. Right next door, separated by inflationary space, universes exist where the concept of matter never had a chance to mean anything. Number 5. The bulk where gravity comes from. In 1998, 3 physicists, Juan Maldacena at the Institute for Advanced Study in Princeton, and building on work by Gerard 't Hooft and Leonard Susskind, developed one of the most mathematically striking ideas in modern theoretical physics, the holographic principle. The basic idea is this. All the information needed to describe everything happening inside a 3-dimensional volume of space can be encoded on the 2-dimensional surface surrounding that volume. Like a hologram on a credit card, a flat surface that contains all the information needed to project a 3-dimensional image. Applied to the universe, this suggests something genuinely strange. Our 3-dimensional universe, with all its galaxies, stars, planets, and people, might be a projection. The actual fundamental reality might be a 2-dimensional surface at the boundary of our universe, encoding all the information that appears to us as 3-dimensional space and time. If that's true, outside the universe in a very specific sense is where the real information lives, the boundary, the screen on which our reality is written. Everything we experience, every physical object, every force, every event in the history of the cosmos would be a projection from that boundary surface. Physicist Leonard Susskind at Stanford has spent years developing this framework and considers it one of the most important results in theoretical physics of the last 3 decades. It is not mainstream science in the sense of being experimentally confirmed, but it is mainstream in the sense of being taken extremely seriously by some of the most technically capable physicists in the world. What lies outside our universe might not be another universe. It might be the screen on which ours is written, and we are the projection, not the original. Number 4. A collapsing region that will consume ours. In 1983, physicists Sidney Coleman and Frank De Lucia published a paper describing something called vacuum decay. The basic idea is that the universe we live in might not be in its true lowest energy state. It might be in a metastable state, stable enough to persist for an astronomically long time, but not truly stable in the deepest sense. Think of a ball sitting in a small dip on the side of a hill. It's stable as long as nothing disturbs it, but it's not at the bottom. A quantum nudge could push it over the edge, and it would roll all the way down to the true lowest point. The universe might be that ball, and the quantum nudge could happen anywhere at any time, including in the space outside what we currently consider our observable universe. In 2012, the discovery of the Higgs boson at CERN allowed physicists to calculate whether our universe's vacuum is stable or metastable. The answer came back: our universe sits in the metastable region, not comfortably stable, not certainly unstable, right on the edge. If vacuum decay has already begun somewhere outside our observable universe, in the vast regions of space beyond what light has had time to reach us from, a bubble of true vacuum would be expanding outward at the speed of light. Inside that bubble, the physical constants are different. Protons don't exist in that form. Atoms can't form. Nothing we know as matter survives contact with it. The bubble would arrive with zero warning. No light, no signal, no detectable precursor could reach us before the bubble itself, because nothing travels faster than the bubble's edge. Outside our universe right now, this process may have already started, and the only reason we don't know is that the information can't outrun what's coming. Number 3. An ocean of mathematical structures. In 2007, MIT physicist Max Tegmark published the mathematical universe hypothesis, one of the most radical and most seriously argued ideas in modern cosmology. The proposal sounds simple. It is not. Tegmark argued that mathematical structures don't just describe physical reality, they are physical reality. Every mathematical structure that's internally consistent, every set of rules that doesn't contradict itself, exists as a real physical universe, not metaphorically, not as an abstraction, actually physically, concretely exists. Our universe is one mathematical structure. It happens to be described by quantum mechanics and general relativity. Other mathematical structures with completely different rules, different numbers of dimensions, different types of particles, different forms of logic are other universes, all equally real, all equally physical, all existing whether or not anything in them is aware of them. What lies outside our universe in this framework is an ocean of mathematical existence. Every possible set of consistent rules, every possible geometry, every possible form of physical law, all of them realize as actual universes somewhere in the space of all mathematical structures. Most of those structures contain nothing recognizable. Some contain complexity of kinds we can't imagine, because our minds are built for the specific mathematics of this universe and have no framework for processing others. Some might contain forms of intelligence so alien that the word intelligence barely applies. The unsettling part is the implication for our own existence. In a space containing every possible mathematical universe, the question of why we exist in this particular one dissolves. We exist here because this is one of the structures that produces observers who can ask that question. But we are surrounded, in some abstract mathematical sense, by infinite universes that contain nothing, and infinite universes that contain things we have no words for. Outside our universe might be everything that mathematics allows, which is everything that can exist. Number 2. Nothing that can be known. This one isn't a physical theory, it's a mathematical limit, and it might be the most disturbing entry on this list precisely because it's not speculative, it's proven. In 1931, mathematician Kurt Gödel published his incompleteness theorems, two proofs that shook the foundations of mathematics itself. The first theorem states that in any consistent mathematical system complex enough to describe basic arithmetic, there will always be true statements that cannot be proven within that system. The second states that no such system can prove its own consistency. What this means for physics is subtle but serious. Our universe operates according to mathematical laws. We discover those laws by observing the universe and building mathematical models that match our observations. Physics is, at its core, the project of finding the mathematics that describes reality. But mathematics, Gödel proved, is inherently incomplete. Any mathematical system we use to describe the universe will contain true statements, real facts, that the system cannot prove or reach. There will always be truths outside of the reach of any framework we build. Applied to the question of what lies outside the universe, Gödel's theorem suggests something specific. Whatever lies outside the universe, whatever physical or mathematical reality contains our universe, may be genuinely, permanently, mathematically unknowable from inside it. Not just unknown with current technology, not just difficult, provably unreachable by any logical system that operates using the rules of our universe. We are, in a provable sense, sealed inside a bubble of knowable reality. The theorems that describe the limits of mathematics also describe the limits of what any intelligence inside our universe can ever know about what's outside it. What lies beyond everything might not just be unknown, it might be unknowable by definition, and mathematics itself is what proves that. Number 1. Our universe is inside something else's physics. In 2003, philosopher Nick Bostrom at Oxford published what has become one of the most widely discussed arguments in modern philosophy and physics, the simulation argument. And unlike most philosophical thought experiments, this one has a mathematical structure that forces you to take it seriously. The argument is this. At some point, any sufficiently advanced civilization will develop the ability to run detailed simulations of reality, simulations complex enough that the simulated beings inside them have no way to detect they're simulated. If even one civilization in the history of any universe ever reaches that point and chooses to run such simulations, the number of simulated beings would quickly dwarf the number of real ones by an enormous margin. Which means, statistically, you are almost certainly simulated. What lies outside our universe in this framework is not another physical reality in any sense we can relate to. It is a computational substrate, hardware, running on physical laws completely different from ours, operated by an intelligence we have no framework to comprehend. Our universe's physical constants, our laws of physics, are dimensions of space and time. All of them are parameters in a program. They are what they are because something set them that way. In 2022, physicist Melvin Vopson at the University of Portsmouth published research suggesting that information behaves like a physical substance with mass and energy in our universe, exactly the property you'd expect if physical reality were fundamentally computational. In 2023, a team of physicists proposed a test for the simulation hypothesis, looking for specific patterns in the cosmic microwave background that would be consistent with computational rounding errors in a finite resolution simulation of space-time. The test hasn't been run conclusively yet, but here's what makes this the #1 entry. Every other theory on this list describes something outside our universe that is indifferent to us. This one describes something that built us, something that decides whether our universe continues, something that could in principle pause it, edit it, or end it without any warning and without violating a single law of physics as we experience them. Because the laws we experience are the ones it wrote.